Exercise 21A, estimating the areas under the curve. Here's a bold question. I've got a graph. I want to find what the area underneath it is in between the x-axis and the graph. Well, often when we have a curve, like a quadratic or a cubic, it's not a regular shape. So how do we find the area? Well, one of the strategies we can do to approximate it is by using other regular, ordinary polygonic shapes and as a substitute, and see if we can make an estimate. Here I've got a curve, and I am going to approximate it by using a thing called a left endpoint estimate, a right endpoint estimate, and the trapezoidal estimate. So what does that mean? Well, the left and right endpoint is a strategy where we use rectangles to be able to approximate the area under the curve. The leftmost indicates that I start from the left of the value. So in this case, we're starting from 1 and we're ending at 5. So start from the leftmost value and I go like this. So similarly here as well. Whereas the rightmost, as you could possibly guess, I start from the right and make my way to the left. So the left and the right endmost estimates will involve some of the rectangles being above the curve, some of them will be underneath the curve, and theoretically we can find an area by finding the average between the two. So what's a trapezoidal estimate? Well, a trapezoidal estimate is when I make a trapezium shapes in between. So this is where we use, if we were to take starting from the left and we follow the curve to make a trapezium. So when I do this, often students find it very difficult to visualize the actual trapezium. It probably doesn't help that I don't draw it very well. But basically, if you imagine it's a trapezium on its side. So if I was to put this on the way that most people might recognize, there's a trapezium. Normally, people would see the right-hand side as being sloped in, but there's the A, and there's the B, and there's the height there. So what we would do is we would make little estimates, trapezium estimates, like so, following the curve. So if it was going the other way, I'd have it pointed in the other direction. So we can approximate these using our area formula. So for instance, for the rectangle one, I would do length times width and add them all together. And for trapezium, I would do 1/2 brackets A plus B, close brackets, times by H. So let's go and have a go at calculating these estimates. So I've done all the areas for all of these, and you can see there that the ones that are over the line are 13.2 square units. Underneath it's 10.2. Closer to the line, we're getting about 11.7. And you could do some averages for each of these. So which answer do we go with? Well, if we're approximating, we can use either of these. However, is there a way we can actually go about knowing the area for real? Well, it's useful to know a few things. One, you'll notice that each of my shapes have got the same width or the same height. In this case, the lengths have all got the rectangles have all got the same width of 1. And the trapeziums have all got the same height of 1. In other words, I'm calculating this for every change in x being equal to 1. Every change in x. Now, where have we seen something about an every change of x? Now, the other thing to be aware of, something to notice, that you could say that when I'm adding all of those rectangles together, it's the sum of. And the sum of is this symbol, sigma, which could potentially be molded and altered and changed. I wonder what into, though. And also, you'll notice here that every of the sort of the lengths that we found was just substituting that x value into the original equation. That's how we got 5, 3.5, 2.5. That is how we got them. So I wonder if that's awfully similar to something we've done recently.